So x is orthogonal to all row vectors, therefore x is in the orthogonal complement of the row space. So what we've shown is that the null space of A is equal to the orthogonal complement of the row space. I won't prove it in this video, but a very similar proof, just essentially working with the transpose of A, shows us that the null space of A transpose is the orthogonal complement of the column space of A. I just want to make one more concluding observation to put all of this together and to make a nice observation. A few remarks to lead up to it. One, what's the orthogonal complement of the null space of A? Well, let me erase these. We saw above that the null space of A is the orthogonal complement of the row space. And therefore, we can take orthogonal complement here and here and conclude that the null space of A, the orthogonal complement of the null space of A is the orthogonal complement of the orthogonal complement of the row space of A. But it was something that we stated in this chapter, that if we take orthogonal complements twice, these orthogonal complements in a sense negate one another, and so this last subspace is just the row space of A. In other words, what we're saying is that the null space and the row space are mutual orthogonal complements of one another in n-dimensional Euclidean space. So we can write Rn as a direct sum. Well, it was a general result that we wrote down early in this section that for any subspace of W in Rn can be written as the direct sum of W and its orthogonal complement. We can take any subspace W and form this decomposition. In particular, if we take W to be the null space of A, then we have the following direct sum decomposition of Rn. Rn is equal to the null space of A plus the orthogonal complement of the null space of A. That's just this observation applied to the null space of A. But then from this remark up here, we know that the null space of A, or the orthogonal complement of the null space of A, is just the row space of A. So one more equality. Rn is the direct sum of the null space of A plus the row space of A. Now, what happens if we write down dimensions? The dimension of Rn is, of course, n. The dimension of the null space of A is, of course, the nullity of A. And the dimension of the row space of A is, of course, the rank of A. And so we again wind up with essentially an alternate proof of this big result that the rank plus the nullity of a matrix is just equal to n. And that's the end.